All right, this is section 5.1 on the Bohr model of the atom, and in this section we're talking about the nature of light. So here's what we're going to try to cover in here. Be able to do calculations that involve wavelength and frequency, also energy and frequency. Later we'll talk about Planck's constant, that's what they're talking about there. And talking about third thing says be able to state the velocity of electromagnetic radiations, know what that is, and then at least 3 different areas of the magnetic spectrum. Let's go back and do a little bit of history. First of all, if you kind of go back to the 1600s, there's a little dispute back then about light. Isaac Newton thought that light was tiny particles, and that the particles would travel like in a beam, like a stream. So that was kind of the belief that he had. Another guy at the same time, a guy named Christian Huygens, suggested that they would be more of a wave. So there's these 2 ideas competing, and they can't decide which is which one is really real at the time. And of course Newton's pretty famous, so a lot of people kind of believe his ideas. Then about 200 years later, a guy named Maxwell comes up with a wave model, and this is a big deal. I mean, people really believe at this time that this is it. They have pretty much done with physics. They don't need any more. They don't even want to send kids into physics because it's pretty well done. Might as well go into some other field because he's pretty much figured it all out. He kind of showed how, electricity and magnetism and all these things kind of work together, and had all this wave model stuff for all that. So, that's kind of what happens in about 1864. Fortunately, physics didn't stop. They did keep looking. And about 60 years later, a guy named Max Planck comes out with some more ideas. And so we're back to this process that we still have this argument, I guess, between is it a particle or is it a wave. And actually today, the belief today is that it's both. There's this duality theory that they actually think it's both of those things. So let's talk about waves, because that's what this kind of section is about. First of all, whenever you see a wave, we're talking about the wavelength. We're always talking about the length from crest to crest, so this distance across here. That's usually the definition of it. Technically, it could be from trough to trough. It could even be from identical points, so like this part is going up on the wave and to another one over there. They're all the same, but usually we say it's crest to crest. When they talk about amplitude, they're talking about how high the wave is above this median, this line that goes kind of this area where if the wave weren't moving, where that would be, think about like a water wave, that'd be where the sea level was if there weren't any waves. And so the amplitude is how high that is at that point. All right, if we want to figure out the velocity of a wave, velocity is the frequency of a wave times the wavelength. So here's the wavelength. That's kind of a weird symbol. We use this weird symbol called lambda, which stands for the wavelength. So velocity is wavelength times frequency. Now, a lot of books you'll see this Greek letter of nu used for frequency. Well, the Greek letter nu looks like a V, and that gets really confusing when we're doing V for velocity, so we're not going to use that. We will use F. So we're always just going to say that our velocity is equal to wavelength, lambda, times frequency, F. And that's what we use. We're talking about the frequency. We talk about the frequency in terms of hertz. And a hertz is really 1 over a second. A lot of times you'll see them write it as seconds to the -1, or they could write it as HC, which stands for that same thing. See, all of these things are writing the same exact thing right there. The textbook, I think, tends to do it this way. I tend to use hertz a little bit more, but any of those is okay. All right, so let's do velocity problem, and what I want you to do is to actually stop the video after I give you this problem and work on it and see if you get the same answer. So if I told you that we have a wavelength of 2 meters and we have a frequency of 10 hertz, go ahead and stop the video and see if you can figure out the velocity. Well, you should know that that's my formula. That's not too hard to do. 2 meters times 10 hertz, and we could say 10 over a second, so 10 seconds to the negative 1. 10 times 2 is 20 meters, and we can put seconds on the bottom. That's what negative means, negative 1 means. So 20 meters per second. Alright, I got another one I want you to do. Try this one. What if we had a velocity of 15 meters per second and a frequency of 3 hertz, or 3 seconds to the negative 1. Go ahead and stop the video and do that problem. Alright, if you solve for the wavelength, which is what we're trying to find here, you know that that's going to be velocity over frequency. So we would put 15 meters per second over 3 seconds to the negative 1. And, you know, if you or divide by negative exponent, same thing, you can move it to the top, make it positive. And so our seconds are going to cancel. Seconds cancel out. 15 divided by 3 is 5, so 5 meters is my final answer. Alright, so let's talk a little bit about these electromagnetic waves. And they're both electric and they're magnetic, and they travel at the speed of light. All electromagnetic waves are like that. And what you see here, this diagram, is to kind of represent, you can see that the blue is representing the magnetic field, and the orange, the electric field, and that's kind of how they draw this out, you know, so you get this wave pattern like this. But understand that light doesn't move up and down like that. Light moves in a straight line. This diagram is to represent those fields as that wave particle moves, either this, you know, whether we're talking about the electric or we're talking about the magnetic. But the light itself would move in a straight line like that. One thing that's different about electromagnetic waves than typical waves that we see on the Earth is that electromagnetic waves do not require a medium. And I guess I shouldn't say on the Earth. We do see electromagnetic waves on the Earth all the time, but they don't require a medium. So they can travel through space, through the vacuum of space. Okay, so like I said, they all travel at the speed of light, don't require any medium. The speed of light, by the way, is 3 times 10 to the 8 meters per second, or 300 million meters per second. And so if we want to figure out, c is usually what the variable that they use for the speed of light. I'm not sure why they picked c, but that's the variable that stands for the speed of light. So instead of v for velocity, we would use c for the speed of light. And c is going to equal our wavelength times our frequency, just like we had before. So velocity equaled wavelength times frequency, and since c is just simply a velocity, same thing. Alright, I want to talk a little bit now about what's called Planck's constant. And anytime we're talking about electromagnetic radiation, since the speed is always the same, the amount of energy that this wave possesses is due primarily or only due to the frequency. The higher the frequency, the more energy it has. And this guy named Max Planck came along and figured out how to calculate that energy. And he used this formula, E equals HF. E stands for energy. Try to spell that right. F is frequency. And H is what he found, and that's his constant. And his constant, H, is 6.6 times 10 to the negative 34. And the label is joules times second. Joules is a form of energy. Joules times second. So energy is in joules. And there's his constant, joules times seconds. And so whichever, the higher the frequency, the more energy you have. And it makes sense. If, you guys all know gamma rays, they're the really dangerous ones. The Hulk, he got exposed to gamma rays. That's what turned him in, green and turned him into Hulk. Those are the highest ones. These have the most energy. And that's why they're the most dangerous. And then next we have X-rays. And X-rays, you know how they can penetrate bone and do all those kind of things, see all that stuff inside your body. That's because they have more energy than than the next ones. And then it's ultraviolet rays. And then we get into the visible spectrum, which is pretty small. And then below that, we have infrared and then radio waves. So the ones with the least amount of energy are radio waves. The ones with the most are gamma rays. Here's visible light, and if you can see, look at this whole spectrum all the way across here. See how big that is? And visible light is just this little bit right here. And then, of course, they expanded it down below. But that's just that little bit that we can see. We can't see too many of those, any of those other rays. And so you can see all the rays that are given here. We got gamma rays, X-rays, ultraviolet, infrared, and microwave I didn't talk about, but they fit right there. Radio waves, and then longer radio waves, and so on. So this is your spectrum. And remember, if you want to kind of think of the energy in the visible spectrum, remember, a lot of you probably remember Roy G. Biv, which is backwards from this thing, but Roy, oops, yellow would be here, green, indigo, violet. So Roy G. Biv is kind of the way to remember the order of all of the colors of light: red, orange, yellow, green, blue. How about we get blue in there? Blue, indigo, violet. Okay. Remember, this side is the low energy side, this side is high. Ultraviolet has more energy. That's why you get sunburned by ultraviolet light, because it has more energy than visible light. And there you have it. That's it.